Alright, we'll get started. Today's lecture is a lot of ground to cover, but we'll start with respiratory mechanics. Mechanics of breathing. Now, I had said earlier that the lung wall stuck to the chest wall, but that wasn't entirely accurate. They actually communicate to this tiny space called pleural cavities. So look what I have on this first slide. There's a bunch of images. Yes, the lung wall is stuck to the chest wall, but not by a direct attachment. It's through the pleural cavity, a fluid-filled space between parietal and visceral pleura. So if you look at the close-up, there's a little gap between lung wall and chest wall. They are indeed stuck through this little space called the pleural cavity. So you should note the pleura. The lung wall is stuck in the chest wall via the pleural cavity. So let me define this little slit of a space between lung wall and chest wall. First you have the parietal pleura. It's a serous membrane that lines the inside of the chest wall, the parietal pleura. Okay? And so you can look at this little close-up view. You can also look at it schematically on this bottom picture here. If the lung is represented by a lollipop, and you insert a lollipop into a water balloon, and the water balloon completely envelops the lung, the lollipop lung is basically its association with the pleura. So the parietal pleura would be this outside of the water balloon. And the visceral pleura attached to the lung will be the inside of the water balloon. So the pleural membranes, parietal and visceral, they're both serous in nature. That's why the pleural cavity is fluid-filled. The parietal pleura lies inside a chest wall. And then you have that gap or space, which is the actual cavity, pleural cavity. The fluid-filled space, because the pleural membranes are serous, and if you were to measure the pressure inside that tiny slit, it's about -4 millimeters of mercury. It's a negative pressure relative to atmospheric pressure of the atmosphere, which would be 0 millimeters of mercury. So sometimes we just use the atmospheric pressure, sea level, here in Sacramento, is a 0 point. Really, it's something like 760 millimeters of mercury. And so if we kind of put it to this, it's like 756 millimeters of mercury. Sometimes I call this the intrapleural pressure. Intrapleural pressure, abbreviated PIP. Intrapleural pressure. Okay, that's the pleural cavity. And it's in between the parietal pleura and then the visceral pleura, which lines the outside of the lungs. I'll say outside of lung wall. Outside of lungs. Okay, well anyways, look at the pleura, look at the lungs. Now in this picture here, it's from the atlas, the blue is the pleura. You can see that the pleura occupy more space in the thoracic cavity than the lungs. So make no mistake, the pleural cavity is filled with fluid. So if I ever ask you what's inside the pleural cavity, don't say lungs, because students always want to say that. I think it's true that the pleural cavities surround the lungs, but they don't contain the lungs. They contain fluid. Okay? And it's very important. This is how the lung wall is stuck to the chest wall. If you were to take a glass plate and put a small drop of water on it, and then put another glass plate on top of it, that little fluid is like the fluid in the pleural cavity. It will be very difficult to pull those two glass planes apart because of the cohesive forces of the water. Maybe you could slide them back and forth like this, but to separate them would be very difficult. You don't want to break that seal. If you were to, you would get a collapsed lung as shown here. Collapsed lung or secondary telectasis is the fancy way of saying the collapse of a previously inflated lung. You first inflate your lungs at birth. If you ever get a wound that breaks that negative seal, that negative pressure, air will rush in to equalize, and then the lung collapses. It could be a wound, it could be spontaneous. So let's say you have a wound that kind of breaks that seal, the pleura are damaged. And let's say in this example, air enters. Air enters the wound. Maybe it's a bullet, maybe it's a knife. That would be a pneumothorax. Pneumo means air. They say if blood enters, that would be a hemothorax. Hemo means blood. In either case, the lung collapses because the seal's broken. Both of these lead to collapsed lung. And, well, you still have the other lung intact because the pleural cavities are separate. That's one thing you'll learn. So that's good. One collapsed lung means at least the other lung is still functional. But you would need help to inflate that lung. If the lung is completely deflated, it's too difficult to inflate. You have to evacuate that space. So you can insert a chest tube to evacuate the air or fluids that have entered that space. So you treat RX, insert chest tube. That would evacuate the air or whatever's in there to help reinflate the lung. There's an emergency situation, it's called tension pneumothorax. Normally, if you have a hole in your chest and air can enter and exit, but a tension pneumothorax is if you create a flap that when you breathe, it allows air in, but then when you breathe out, the air is trapped, tension starts to build, and that's an emergency where you would have to treat in the field, and you probably wouldn't make it to the hospital. But in either case, the air or fluid must be evacuated. Now, collapsed lung, I want to talk about the regular muscles of breathing, okay? And I want to start with the diaphragm. The diaphragm is your major muscle of inspiration. Oh, before I completely erase this, if pressure was -4, let's say, let's put this in a sealed place. I know it's not a circle, but just for illustrative purposes. Let's say you break the seal, air rushes in, but the air outside the balloon is 0. When air rushes in, what does this become? 0. Okay, and that's something that students frequently miss on the test. You're just equilibrating with the atmospheric air when the lung collapses. So look at the anatomy of the diaphragm. Diaphragm means membrane. This membrane separates the thoracic cavity from the abdominal cavity. Membrane. Diaphragm means membrane. Separates thoracic cavity from ab cavity. So anatomically, it's that barrier, that membrane. And well, things must go through it to enter and exit those cavities. For example, you should know at the level of T8 vertebra, there's the cable opening. And through there goes inferior vena cava. I'll point to it. It's the highest hole. On the bottom, it's right there. But on this picture from the side view, it's right there. At the level of T10, you have the esophageal opening. It's right there. The esophagus goes through there to get down to the stomach. T10 vertebra, esophageal opening. I won't even say what goes through it because the name of the opening tells you, right? The esophagus, the food way. At the level of T12 is the aortic hiatus, right there. At about that level, that's where the aorta goes through there and becomes the abdominal aorta past that point. The level of around T12 vertebra, aortic hiatus. That's where the aorta becomes abdominal aorta. Now the diaphragm is a big dome. So let's start to talk about its function. Look at the central tendon. If you look underneath it, all the muscle fibers are arranged in a circle around the central tendon. So when they all pull all the way around, they pull the tendon down. So when the muscle contracts, it flattens to this reddish zone. That helps to increase the thoracic volume during inspiration. This is the main muscle of breathing during inspiration. Main muscle of breathing during inspiration. Now the nerve roots that control the breathing come from cervical spinal nerves, C3, 4, 5. Keep your diaphragm alive. C3, C4, C5. Those nerve roots form the phrenic nerve. That's one of the most basic anatomy questions. The phrenic nerve innervates the diaphragm. So the diaphragm contracts, it flattens, it increases the thoracic volume to draw air into the lungs. So it contracts. That's its function. Flattens. Increase thoracic volume. At the very same time, you decrease intrapulmonary pressure. I do abbreviate that lecture, capital P, small pull, intrapulmonary pressure. And that will help air flow into the lungs. You're creating a negative pressure inside the little alveolar spaces just by expanding your chest cage. We have one of these cadavers, it's like cut in half. Right there, you can kind of see that. You almost stick your head up there. It's very large domy space is what I'm trying to say. All right, I have this picture to remind me of the other muscles of breathing. You know, any muscle that actually has attachment to ribs can help you breathe. Well, diaphragm is one. The external intercostal is the other major muscle of inspiration. The external intercostals occupy all these spaces. They run all the way up to right around the border between bony rib and cartilage, costal cartilage. So note the external intercostal as another muscle of inspiration. So another main muscle of inspiration, also external intercostal. Costals, plural. I mean, they occupy all the costal spaces. Okay? It's not just one, it's all of them. Because each one is lifting up the rib below it. So the action of this muscle is to elevate ribs. So let me erase, start at the top. They kind of call the elevation of ribs a bucket handle movement because a rib is kind of curved like a bucket handle. So I just lift it up a little bit. Like lifting a bucket handle. That helps kind of expand the rib cage side to side. You know, laterally. Now if you look at the next slide, it kind of shows the bucket handle movement. Like right there. These ribs, set of ribs, just lift them up just a little bit. And if you look at it from the overhead view, it's easy to see that you're kind of expanding the chest cage just a little bit laterally. You can also expand the rib cage from front to back by this pump handle movement of the sternal angle right there. Like a pump handle. If you crank the pump handle up, it's like expanding the rib cage just a little bit from front to back. So that's the action of at the sternal angle. You have the pump handle movement, where you expand the rib cage anterior to posterior. So every time you take a breath in, that's kind of what's happening. Now to go back to the previous slide, there are other muscles that help you breathe. Now normally when you take a breath in, you do recruit muscles for that. Most notably the diaphragm and the external intercostal. But exhaling your air, expiration, that's normally a passive process that does not require muscle recruitment. But if you're really huffing and puffing, say during a strenuous workout, and you do need to recruit muscles to help depress ribs, and that's the internal intercostals right here. Internal intercostals depress ribs. Any muscle that has attachment to ribs can be considered a muscle of accessory inspiration. Muscles of accessory breathing. Okay, I'll just define it as any muscle that attaches to ribs. On this picture I have, like for example, at the top, look at those neck muscles called the scalenes. They attach to the top two ribs, so they can help breathe a little bit. So I'll list them as a muscle of accessory breathing, the scalenes. You have serratus anterior. It attaches to ribs 1 to 9. You have all the pec muscles. Pec major, pec minor, for example. I'll just list that one. It has attachments to rib 3 to 5. Sternocleidomastoid. Doesn't really attach to ribs, but attaches to the clavicles. That can help you breathe too. And it also attaches to the manubrium. So those are just a few. But the main ones are diaphragm, internal, external, intercostals, the main muscles of breathing. So the mechanics of breathing can also be understood if you understand the gas laws, because we're talking about airflow in and out of the system. And so the one thing you should remember from chemistry is that gases, anything in a gaseous form is going to fill the chamber that you've sealed it in. And then so gas molecules are not like lipid molecules. Gas molecules will fill the volume of the chamber they're in. So if they're in a liter of volume, let's say this example, this gas is exerting 1 atmosphere of pressure. If you kind of compress the volume, you double the pressure so that this law, Charles' law, I think, was Boyle's law. Can't remember right now. But the point is, it stays equal. If you have the volume, you double the pressure so that the law stays true. These gas molecules have half the volume to bounce around in, so they exert double the pressure. That law, well, we don't really directly apply that law, but it's important to realize, because you do want to change the volume of the lungs so you can create a gradient for air to flow in and out of the lungs. I think that much you do need to understand. So the physics of all this, the lungs, the airways, the chest wall, all that, how they cause changes in lung volume, which creates pressure gradients, and those gradients will get the air to move in and out of your lungs. And so to kind of like take you through this, step by step, we define these pressures across the system. If there's a pressure difference, air will flow. If there's no pressure difference, air does not flow. Can't be stated any simpler than that. If air is not flowing, are you breathing? No. That's an easy no. Well, anyways, to put it in kind of a term, I got to define all these. I think I defined them already. Well, just to recap. Pressure in the atmosphere at sea level, 0. Okay? Millimeters of mercury, if I ever don't say it, it's understood. That's our 760, right? That's our baseline. But what I said was the pleural cavity always has a negative pressure. On average, it's -4. PIP. Or 756. Now that intrapulmonary pressure, that is always changing with breathing. People, as I abbreviated it, intrapulmonary pressure. If you ever see it called intraalveolar pressure, same thing. But anyways, it's like 0, +1, -1. It changes with breathing. The point is that we breathe by negative pressure. A negative pressure means air will flow into the lungs. That's inspiration. If you create a positive pressure with respect to the atmosphere, air flows out. And if you calculate no difference between the inside and the outside, no airflow. Okay, so I said calculate. The calculation you got to make is the transmural pressure across the whole system, like shown here, PTR. Transmural pressure, the TR is transmural, it's always a pressure in minus a pressure out. However, by our convention, the inside pressure is the pressure inside the intrapulmonary, the intraalveolar pressure, so the people. And the pressure out is the air you breathe, pressure of the atmosphere. And that's our PTR, our transmural pressure. Pressure is always a difference between two locations. When we talked about it in the baroreceptor reflex, that was the pressure across the vessel wall. This is the pressure across inside and outside the lung, basically. Okay. So we're going to ignore PIP. Just know that it remains negative. We're concerned about air rushing into the lungs and rushing out. So we have to consider what the lungs and what the chest are like, because they're like stuck to each other and they have to affect each other for breathing. So we have to define what are called the intrinsic forces acting on lung and chest wall. Intrinsic forces. There's that word again. Intrinsic just means what are the properties of this thing? And this is the lung. The lung is like a balloon. I even have this bell jar balloon lung example I'll go over in a second there, but like if you blow up a balloon but don't tie it off and just let the balloon out the end that you haven't tied off, the balloon will collapse because the balloon wall is rubbery and elastic. It just wants to collapse. So we say that the forces acting on the lung wall are inward acting forces. I'll just say in. In means lung collapses. So I said the lung holds the chest wall in, the chest wall holds the lung out. Forces acting on the chest wall are opposing. They act out. Chest wall. Just think about your rib cage. I'm just using words in and out, but what do I really mean? Your chest wall is a stiff cage. Look at the rib cages on those skeletons back there. I've seen paramedic students give chest compressions to cadavers, and if you do it correctly, you break the ribs, and I hear them crack, crack, crack. Is that something that wants to collapse? The lung does, but the stiff rib cage does not want to collapse. It resists collapsing. It's a stiff, cone-shaped cage. And so that's why it's really good at holding the lung out. Or vice versa. That's why the lung is good at holding the chest wall in, however you want to think of it. Anyways, these are the intrinsic forces of lung and chest wall and how they interact. And so for the chest wall, for the lungs, let's do that first. There are two forces to consider that make it act like a balloon. One are the elastic fibers I showed you that surround the little alveolar spaces. So consider that. I usually abbreviate it EL, these inward acting forces. Elastic fibers. I mean, chest wall forces have an elastic recoil too, but the stiff ribs just act in an equal and opposite direction. They're not a force in, they're a force out. Stiff rib cage. And so the elastic forces are like different. These are a force in, these are a force out. They have to expand the lung and chest wall out. Now the second thing I list for the recoil forces, ST, surface tension forces. That's due to water. These also help collapse the lung like a balloon. When you breathe in air, it's warm and humidified, and that wet air, the water molecules line the alveolar spaces. These little blue dots say, let's let them symbolize water molecules. And because they're arranged in the circle, the cohesion of the force between water molecules, because they're arranged in a circle, they're attracted to each other, but then that creates this inward force that wants to collapse the tiny air sacs in your lungs. So what can help break the surface tension are surfactants, which are similar to the molecules in detergents that wash your clothes. Now let's remember that these are secreted by the type 2 cells in the alveolar spaces. And the surfactants are simply water, they interact with the water molecules by jamming themselves in between them. And by doing that, they break the surface tension forces to make the lungs easier and more compliant to fill with air. Break surface tension. I'll say break ST forces. Makes the lungs easier to breathe. So that's how you're making water less viscous. You're thinning out water, okay? And that's why it makes it a good ingredient for detergents, because by making the water less viscous, the water molecules are more likely to penetrate your fabrics to get the stains out, okay? Here's another way to visualize the lung and chest wall counterbalancing each other. If everything's in equal harmony, the springs are pulling in opposite directions, they'll stay stuck to each other because of that little bit of fluid in the pleural cavity. Okay? But if you breathe in and your chest wall expands out, those forces are greater and it pulls the lung out with it, expanding the volume inside the lung. That draws air into it. But then when you take a breath out, the lung wall forces are greater. So it's kind of like this back and forth, this spring action happening. Breathe in, breathe out. And so that's kind of what you have to consider when you think about these forces and pressures interacting with each other during breathing. Okay, so what we're going to do now is, we talked about, well, here, let me just try that one. We're going to apply the relationship of transmural pressure. Apply. That's that PTR equation. Transmural pressure, pressure in, pressure out, right? But for us, it's going to be, because it's the respiratory system, pressure inside, people minus pressure of the atmosphere. That equation. So we got to apply that relationship of the transmural pressure and the intrinsic forces I just defined. Acting on lung and chest wall. And whenever I say chest wall, just think rib cage, right? That's what the chest wall is. Now I have, normally we think of breathing as breathe in, breathe out, 2 parts. Let's consider a third part. Number 1, FRC. Let's consider the moment before you take a breath. Breathe in, breathe out, pause. Let's think that pause is what I call FRC in this lecture. I'll define FRC later. It stands for functional residual capacity. It's the amount of air that's in your lungs after a normal breath out. Because if you take a normal breath out, I can push more air out. But there's a volume of air I cannot get out of my lungs, unless I collapse my lung. But I don't want to do that. But the point is, at FRC, there's still air in your lungs, but it's just a moment before you take your next breath. So let's kind of start there. Let's talk about intrinsic forces on lung versus chest wall. So the forces over here, transmural pressure over there. So at FRC, nothing moves. The moment before you take a breath, nothing moves, right? The chest wall isn't moving because you haven't inspired air yet. You haven't made that effort to take a breath. Well, that means the forces on the lung and chest wall are equal opposite direction. So physics says if this force equals that force and they're in opposite directions, there's no movement. You don't have to take a physics class to understand that. Forces acting in equal and opposite directions, there's no net movement. And so if we were to measure our equation here, transmural pressure, the intrapulmonary pressure right before you take a breath is actually 0. It has equilibrated with the atmospheric pressure, which is also 0. So it becomes a very easy calculation because 0 minus 0 equals 0. What's the concept here? I mean, why would I tell you that? We're measuring the difference between air outside and air in your lungs. If there's no difference, there's no airflow. Right? This is before you breathe. That's what I want you to understand. 0 gradient means no airflow. You're not breathing. The moment before you take a breath. So when you actually take a breath, on average, you breathe something like 12 to 15 breaths a minute. Sometimes, I'm sure maybe you'll be asked to record respiratory rate. Just watch the chest rise and fall and just count per minute. Should be about 12 to 15. All right, so inspiration. Underline that it's an active process. When you're inspired, something goes into you, right? To do something. Well, when we're just breathing, air goes in. It's an active process, which means, in physiology, active means recruit those main muscles of inspiration. Diaphragm, the external intercostals, not scalenes. I don't know why I listed them there. They do help you breathe, but let's go with the first two. Those are the main ones. Recruit muscles of inspiration. Diaphragm, external intercostals. All right, so when you do that, when you got the muscles working, and you expand the rib cage, and you flatten the diaphragm, you expand the rib cage. So what I'm telling you is the chest wall forces are greater than the lung forces. Okay, so those are the intrinsic forces during a breath in. So what you're doing is you're expanding the thoracic volume. Increase thoracic volume. Therefore, decrease intrapulmonary pressure, the peephole. It kind of happens simultaneously. So if you calculate our transmural pressure, PTR equals peephole minus pressure of the atmosphere, you create a negative pressure of about -1 millimeters of mercury. Minus 0, which is pressure of the atmosphere. So -1 minus 0 is -1. But you don't need a calculator for this math. It's more of the concepts. And so by convention, -1 means what? Is air going to flow in or out to make things equilibrate? Air will flow in until it reaches 0. Then you have equilibration. I'll say air in, right, until 0. Then air stops. Because then the 0 equilibrates with the air you're breathing in. Well, that's pretty much it. That's the point. You've created a little bit of negative pressure to draw air into your lungs during the breath in. So I have this animated right here. So let's pretend this is FRC, the moment before, where everything's equilibrated, 0. It's 0 on the inside, you assume it's 0 on the outside. You take a breath in, you expand the thoracic volume, you expand the lungs with it. That decreases the pressure inside the alveolar spaces to -1. Air rushes in to fill that vacuum until it equilibrates. Okay? So now one more time. So it's 0, and it changes to what? -1. Air rushes in until it equilibrates. So I animated so the -1 happens first, then you draw air in. Really, they're happening simultaneously, but I want you to think the negative pressure is the cause of the air coming in. Okay, you're not inflating the lung. You're breathing by creating a negative pressure first. Now, taking a breath out is simply the opposite, but it's a passive process. Normal quiet breathing is like you're doing now. Passive means no muscle recruitment. Unless you're huffing and puffing during a strenuous workout, then you might be using it. But okay, let me erase. Let me write this right. Passive process. So just think of it this way: muscles relax and the lungs recoil. Muscles of inspiration relax. That allows the lung forces to be greater. The lungs will recoil, and the lungs will always go in. The lung is like a balloon, so these forces are greater. So I'm going to change this arrow to go this other way. Now the lung wall forces are greater than chest wall forces, and the lungs recoil. So what that does is the reverse for this. I'm just going to change these arrows. Okay, you say it with me. If your chest wall is collapsing, what's happening to the thoracic volume?
Decrease.
Down. And if you're decreasing the volume, the pressure inside the alveolar spaces are increasing a little bit. And they increase to something like +1. Right, so now we've just created the opposite gradient. Now air will just flow out. So the +1 means air out until you equilibrate to 0. And that's all it is in terms of the math, but I did an animation. So this is the moment before expiration. So we're at 0, and then you kind of collapse and create a positive pressure to push air out. And so kind of look at it in graph form. Look at the top graph. Well, actually look at all three, but look at the top graph especially. So what does that mean? When I say especially, look at this one. You're going to see it again. Well, I'll go through all three of them. Look at the PIP. Now, what did I say? What is the number I had you write down for that pressure? The PIP, the intrapleural pressure. -4. Now, you can see it's not a straight line, -4, but it does change with breathing. But the point is, on average, is -4. It stays negative with relative to atmospheric pressure. That's the main thing to understand about intrapleural pressure in my lecture. Now this, here you got to know. So, all right, so what I said was, this is FRC before you take a breath in, you're at 0. Look at the green dot and follow that with the animation. So if you take a breath in, you create negative pressure. So that's why you drop to -1. Then what happens? Air rushes in until you equilibrate. So at the end of a breath in, you equilibrate. And it's the same thing for the breath out. You collapse, create a positive pressure, the positive one, then air flows out until you equilibrate again. So breathing's easy if you have surfactants. The surfactants mean you only have to generate just 1 or 2 millimeters of mercury gradient to get air to flow. Easy breathing, you don't even feel it. But if breathing is labored without surfactants, you would have to generate 10 times the pressure gradient. Okay. So, just to review really quick, before you breathe, which force is dominant, chest or lung? They're equal. Neither dominate. But which dominate during a breath in? Chest. That's why you recruit your breathing muscles, to expand the chest. Well, what about during a breath out? Lungs. That allows air to be pushed out, and the lung pulls the chest wall in, so we think of it that way. So for the bell jar model, let me just kind of show it to you right here. So in this model, what do the balloons represent? Lungs. Now this stopper has a hole in it, so that represents the airway. What does this rubber thing represent? Diaphragm. Now I can pull up and down on it. If I pull down, what does that do to the thoracic volume? It increases it. So that, what should happen to the balloons when I pull down? You should decrease the intrapulmonary pressure, air should flow in. So I'm going to kind of pull down, see how that, let me do it again. Pull down, see how the balloon's inflated a little bit? Now, was I blowing into it? No, I just pulled down, that's all I did, and air flows in. Now what happens when I push up? I decrease the volume in there and should push air out. So see how you're breathing there? So this simulates breathing. You can even hear the air whooshing in and out. So that's why this is a good model for breathing. You can look at that if you want. If it works for that, it certainly works for our anatomy. Well, other things to consider are airway resistance. Let's look at that. Okay, look at the graph and look at the equation. The graph is the anatomy. Remember when I went through the bronchial tree, I said division 0, trachea. Division 1, 2 primary bronchi. Division 2, 5 lobar. Division 3, 18 tertiary. I went through all that. 1 to like 23 or 24. So what we're looking at here, airway resistance, capital R, right? It's still friction. Friction is still the main cause of resistance for air to flow too. But we'll talk about other things. I mean, airflow F is still a function of delta P over R, okay, right? So airflow is inversely related to resistance. If resistance is low, flow is good. That's kind of what we want in this system. Now, we did this, the delta P, like when you change the intrapulmonary pressure to -1, 0, +1. So we did that. When you change that pressure, you cause air to flow. This one, besides friction, we'll talk about the diameter of the airway. The relationship is if you decrease the diameter of the airway, you increase the resistance to airflow. Generally, that's true. So decreased diameter, increase capital R resistance. I mean, that makes sense. There's a smaller space for air to flow through. Can't blow air through a bigger caliber straw versus a tiny straw. It's harder to do. Okay, well, let's start to look at the anatomy. Notice the first several divisions. As the airways get smaller and smaller, do you see why there's an increase in resistance to airflow? But when you get to a certain point, there's a huge drop-off. Now, what could explain that? Even though the airways are getting smaller, what's happening to their overall numbers? They're increasing dramatically. I didn't map out all the numbers, but you start off with one trachea. But when you get deep into the lungs, 10, 11, I mean, you get into like tens of thousands of airways. You get up into the millions of airways, as many as 300 to 600 millions of airways by the time you get to the dead end here. Okay. So even though the airways are getting smaller, after the medium-sized bronchi, you get a huge drop in resistance because of the shear numbers. And so by the time you get to the respiratory zone, there's virtually no resistance to airflow. So respiratory zone. The airways are so numerous, there's no resistance to airflow. Airways are so numerous, there is no resistance to airflow. All right, this is a good spot for a break. Come back at 12:30. We'll continue on with these slides.